Here I have a graph of heat versus temperature. Now, if I were to ask you what this graph looked like, why don't you pause, think about that, maybe draw a little graph in your notes. Most people would say that the graph looks something like this. Okay? As you increase the heat, you increase the temperature in a linear fashion. Most people logic would dictate that it's a direct relationship. However, there's an issue with this. The graph does not actually make a straight line. There are points where you have level areas. Haha. Okay, so let's talk about what's going on here. Let's call this region A, region B, region C, region D, and region E. Okay, and maybe as a clue, if we're talking about water, this temperature is 0 degrees Celsius, and this temperature is 100 degrees Celsius. Now that might clue you in as to what's going on. Okay, if you remember back to the lab that we did with the pressure and temperature relationships, a lot of people really struggled to get down to 0 and really struggled to get to 0. Like, nobody could do that. So let's talk about why. In region A, okay, we have ice. All right, and as I put heat in, I'm getting a temperature change. All right, so the heat the heat gained or lost by this point is Q equals the mass of the ice times the specific heat of ice. Now remember, this is a different value than the specific heat of liquid water, times the change in temperature. MCP, Q equals MCP delta T over this region. But once we hit 0 degrees Celsius, when I add more energy, I actually don't change the temperature. Okay? What happens is, as I'm adding energy in, I'm breaking up some of these really strong interactions, and I am now making a liquid. Okay? So in B, region B, something interesting's happened. We're not getting a temperature change, so I can't use Q equals MCP delta T. The heat is given by a different equation. Okay, Q equals mHF. M is still mass, okay, and HF is the enthalpy of fusion. Okay, now if I think about this logically, Q needs to be in the units of joules. The mass needs to be in units of grams, which means HF would have to be in the units of joules over grams. Okay, and HF is something that you can look up in a table. All right, so that's region B. Now we're back to region C, and now we've got liquid water. And when I add heat, I get a corresponding temperature change, and they're directly proportional. So I'm back to Q equals mass of the water times CP of liquid water. Remember, this is a different value now, times the delta T of liquid water. Okay? So this is just another standard region. You're changing the amount of heat, and you get a corresponding temperature change. Now we get to D. Okay, D is when water turns into water vapor, so this is vaporization. All right, so again, no temperature change. Q equals the mass of the water times HV. And HV in this case is enthalpy of vaporization. Okay, enthalpy of vaporization over this range. So now we're breaking the hydrogen bonds, the intermolecular forces, between the liquids so that that substance can become a gas. All right, now I didn't quite draw this correctly to scale, but the enthalpy of vaporization is going to be a much larger value than the enthalpy of fusion. Okay, so that's just something to keep in mind. And then we're back to E. And E, we have steam, okay, or gas. And we're back to a region where we add energy, and we get a corresponding change in temperature. So we're back to Q equals mass of the sample times Cp of the gas. Okay, remember this is a different value. Notice that I'm highlighting this. This is very, very important. Times the change in temperature of the gas. Okay.